Hey AI enthusiasts, welcome to All About AI Tech. Today, we're tackling a subject that's as crucial as it is complex, algorithmic bias. You've probably heard the term thrown around, but let's get a really clear understanding of what it means. Essentially, algorithmic bias is when an AI system, trained on data reflecting existing societal biases, makes decisions or generates outputs that are unfair or discriminatory towards specific groups of people. Think about it. AI isn't inherently biased, but the data it learns from is often already skewed. It's like teaching a kid about the world using only a biased textbook. The kid might well learn inaccurate or unfair information. We've seen this play out with resume screeners favoring male candidates, loan applications being unfairly rejected, and even medical diagnostic tools that deliver inconsistent results based on race. For instance, a facial recognition algorithm trained primarily on light-skinned faces might drastically underperform when identifying individuals from marginalized ethnic communities. We are actually talking about life and death decisions. Just last year, multiple AI-powered cardiovascular risk predictors were shown to be wildly inaccurate for populations of Black individuals, generating huge concerns about its potential uses within large healthcare organizations. The images for this section will be shocking. We will show a side-by-side screenshot showcasing how AI systems have generated bias outputs which have been cited in press from various countries. We'll see examples of how these biases can create real-world problems and what's being done to fix them throughout the video. Now, let's break down the different ways bias can sneak into AI systems. We'll cover three key types of bias: data bias, model bias, and deployment bias. Data bias refers to the inherent issues in datasets themselves. This can be an issue with even carefully curated datasets, as it's often difficult to completely eliminate bias from even well-intentioned researchers. The initial data will reflect whatever existing inequalities are already present in society, such as wealth, access, and power imbalances, or other historical patterns and assumptions. This means that the AI will inevitably take on these biases in whatever decisions these AI algorithms then make, simply because that's what the algorithm has learned. Model bias is a bit subtler. It's about how the mathematical model is trained and used. Imagine you have a perfectly balanced dataset. Sounds good, right? But if there is an additional constraint in the algorithm, this might produce biased outcomes. This can be especially pronounced in highly optimized AI systems used in high-stakes domains, such as criminal justice. Even small tweaks aimed at improving performance can lead to a systematic favoring of one group over others. This type of model bias can be very difficult to detect. We'll explore some examples in later sections. One of the best-known ones is deployment bias. Essentially, the model is performing as expected if the algorithm and dataset are correctly specified and perform well in the testing environment, but the reality is considerably different. The reason this happens is typically that the testing environment differed significantly from where the model is then actually deployed. This can lead to unexpected results due to an unrepresentative sample for training, insufficient data to effectively account for all the variation in the data observed in real life, or the evolution of model performance, such as when a new competitor appears on the market, as can be particularly pronounced in financial services. The images for this section will show a clear flowchart of how biases are built in, along with some examples. So now we know bias can creep in during design, data preparation, and even application, but how do we actually measure it? Enter fairness metrics, quantitative tools designed to assess if an AI system is treating different groups fairly. Now it's worth noting that even defining fairness is tricky, with different definitions and metrics being employed based on context and industry. We'll focus on what are the three most prevalent ones in this video. The first is statistical parity difference, or the raw difference in outcome between groups. For instance, if a loan application algorithm approves 50% of white applicants and 40% of Black applicants, the difference, that is, 10%, reflects a statistically significant disparity. Pretty easy to understand, but sometimes the simplest is the best. This sort of raw difference may make it easy to show bias, but doesn't account for other factors, which could drive what happens with this metric. The second is equal opportunity difference, which focuses on equal treatment based on the individual's true class. This is a lot more nuanced, as it aims to gauge whether qualified individuals are treated fairly, regardless of their group membership. Let's say the AI is supposed to predict people with a higher risk of a particular disease. Equal opportunity difference attempts to measure whether such an AI model is identifying those at risk equally well across different demographic subgroups, even if the underlying population is not balanced or differs between groups. We'll be showing examples here of how this is calculated in practice. Finally, average odds difference looks at false positive and false negative rates across groups. It tries to capture the relative bias of the algorithm for identifying both positive and negative outcomes. This is useful in situations where both identifying we'll be showing a clear illustration of each of these in practice and how to interpret these metrics during this section. Okay, so now we can measure bias, but how do we actually fix it? That's where bias mitigation techniques enter the fray. There are many ways to approach this challenge, and we'll walk through 3 of the most prevalent ones: pre-processing, in-processing, and post-processing. Pre-processing methods modify the dataset before the algorithm is trained, altering the input to make it fairer. Think of it as cleaning up the ingredients before you start baking a cake. If you have a biased recipe, you might clean up the ingredients, the data, ensuring that whatever comes out is well balanced. Techniques here include things like reweighting, giving more weight to underrepresented groups in the data, resampling, oversampling underrepresented and undersampling overrepresented groups, and removing correlations with sensitive features, such as removing a feature that is highly correlated with race, gender, or other sensitive attributes that are deemed undesirable. We'll show examples of each using various tools, and also discuss some of the pros and cons of each. In-processing techniques alter the learning algorithm itself, such as training an adversarial neural network, adding fairness constraints to the optimization process, and using techniques like disentanglement to train the models in such a way as it can separate the prediction from sensitive information. It's like baking with special kneading techniques. In this case, we have better control over the fairness of the output, while maintaining the quality of the final product. We'll show the results of comparing models trained with and without fairness constraints and compare these results to our fairness metrics. Lastly, post-processing methods adjust the algorithm's output after the model is learned, ensuring that the final decisions are fair. This is somewhat akin to adjusting the icing of our cake, applying mathematical adjustments post-processing to improve fairness across groups. This includes things like calibrated equalized odds and equalized odds. Keep in mind, however, that academics have warned that post-processing methods can lead to much higher performance degradation and should only be used with great care. The visual content will be a flowchart showing how these 3 types of mitigation methods operate in the context of different machine learning algorithms. Let's shift gears and talk about the legal side of things. Governments and regulatory bodies around the world are grappling with how to regulate AI to prevent discrimination and promote fairness. This is a particularly hot topic, with the debate often revolving around whether to emphasize regulations or whether to instead focus on industry standards and voluntary certifications. The European Union has taken a proactive step with its Artificial Intelligence Act, AI Act, which classifies AI systems based on risk and implements quite stringent requirements for high-risk systems. This initiative, which has been praised as a model for global standards, will likely affect how many industries build and deploy AI in the coming years. The AI Act sets a high bar for transparency and accountability, with specific requirements around bias mitigation. The U.S., on the other hand, has pursued its own set of approaches regarding AI governance and regulation, focusing more on providing guidelines and recommendations, along with self-certification processes. We'll discuss different regulatory frameworks, including examples from the UK, EU, and the US, along with some of the advantages and shortcomings of each. We'll also examine the impact of emerging laws and regulations on companies working in different industries. We'll look at examples of how these regulations are affecting AI development and deployment, and some of the challenges in enforcing these rules. The images in this section will show maps showing countries. As we wrap up this exploration of AI fairness, let me reiterate that building fair and unbiased AI systems is not merely an ethical undertaking, but a crucial requirement in the responsible application and advancement of AI systems in the coming years. It's about ensuring that AI works for everyone, promoting it. From a practical standpoint, addressing these issues requires a multi-pronged approach and will not be an easy challenge to resolve. This involves rigorous research into fairness, developing more effective bias detection tools, implementing strong regulations, and creating a system that promotes transparency and accountability. That includes fostering a culture of fairness at every level involved in AI development, from model developers to end users. This requires ongoing commitment among all stakeholders, from governments and regulators to companies, educational institutions, and individuals working within and using AI for decision-making. Working towards AI fairness will not only enhance the integrity of AI systems, but also increase their public trustworthiness, which will subsequently positively impact their broader adoption. Ensuring that AI systems are both usable and just requires consistent and proactive efforts. And there is also some positive news. Research in AI fairness is showing tremendous progress, with new tools, techniques, and algorithms that can effectively assist us in detecting and mitigating bias and promoting fairness throughout the AI and ML model lifecycle. Moreover, with the implementation and enforcement of more stringent regulations, there is reason to be optimistic that new standards and practices will be developed that promote a fairer world for all. I also want to thank you very much for joining us today for our detailed analysis. I hope you found our treatment of the topic of AI fairness both fascinating and illuminating. And if there are any comments, questions, or topics that you would especially like us to cover, please do not hesitate reaching out to our community and our team. We deeply appreciate your ongoing participation and belief in our work. Until next time, stay tuned to All About AI Tech for more insights into the exciting and evolving world of artificial intelligence.